Example 1. The weights of pennies minted after 1982 are normally distributed with mean 2.46 grams and standard deviation 0.02 grams. What is the probability that in a simple random sample of 10 pennies minted after 1982 we obtain a sample mean of at least 2.465 grams? In any word problem, we'll list the variables and we will list our unknowns. We know that the mean of the population is 2.46 grams. So mu equals 2.46. We know the standard deviation is 0.02. Sigma equals 0.02. We are looking for the probability that a simple random sample of 10 pennies, this 10 pennies represents our sample size, and we want to know what is the probability that the sample mean is at least 2.465 grams. That's our actual question. We want to find the probability that the sample mean is at least 2.465 grams. We'll use our formula. Z equals x bar minus mu divided by sigma over the square root of n to calculate this probability. I am going to convert this x bar into a z-score, and then we'll be able to use our z-table to calculate the area, or the probability. We have z equals x bar, the sample mean, in our case is 2.465. So z equals 2.465 minus the mean, which we know is 2.46, and we'll divide that by sigma, which is 0.02, and divide that again by the square root of 10. Z is equal to, let's get started again. So we'll go to our z table. We'll go to our z-table and look for 0.79 for the z-score. 0.79 is located here. So we have the area to the left is 0.7852. 0.7852. And of course we have to subtract from 1. We have 1 minus 0.7852 is equivalent to 0.2148, and this is our solution. What this is saying is we have a 21.48% chance of selecting 10 pennies whose average is at least 2.465 grams. Example 2. Suppose that the mean time for an oil change at 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. Part A. If a random sample of n equals 35 oil changes is selected, describe the sampling distribution of the sample mean. Well, the sampling distribution has to be normally distributed because we know from the central limit theorem that the sampling distribution will be normally distributed. Part B. If a random sample of n equals 35 oil changes is selected, what is the probability the mean oil change is less than 11 minutes? We'll start by listing what we know. We know the mean of the population is 11.4, so mu equals 11.4. We know the standard deviation is 3.2 minutes, and so sigma equals 3.2. N is equal to 35. And now we want to find the probability that the sample mean is less than 11 minutes. So we're looking for the probability that x bar is less than 11. We'll use our formula, z equals x bar minus mu divided by sigma over the square root of n, to convert this into a z-score so we can use our table. Z is equal to x bar. In this case, we want to find a sample mean that's less than 11, so x bar is 11. We will subtract the mean, which is 11.4, divide that by the standard deviation, which is 3.2, and divide that by the square root of 35. We'll type this in our calculator, and we get a value of z equals negative 0.74. And so this means we're actually looking for the probability that z is less than negative 0.74. We converted a sample mean into a z-score. And now we can use our table to find this area. The z-score we're looking for is negative 0.74. And so here is our area, 0.2296. The probability of z less than negative 0.74 is 0.2296. This means if we select a random sample of 35 oil changes and take the average, we have a 22.96% chance that the average will be less than 11 minutes. Now, if some of you are having calculator issues, make sure you put parentheses on the top and the parentheses in the denominator so that you get the correct output. So make sure that you do get negative 0.74 with your calculators. In example 3, suppose the lengths of pregnancies of a certain animal are approximately normally distributed with mean of 148 days and a standard deviation of 14 days. Part A, what is the probability that a randomly selected pregnancy lasts less than 143 days? For this question, we want to find the probability that X is less than 143 days. For this problem, I'm going to use technology. Here we have that we're only selecting one individual, so n is equal to 1. X is equal to 143. And our standard deviation we know is 14. And our mean is 148. In part A, I enter the mean of 148, the standard deviation of 14, and I want to select the below option and enter 143. Now, we have our solution is 0.3605. We have a 36.05% chance that a randomly selected pregnancy will last less than 143 days. In part A, we have the probability that X is less than 143 days is equal to 0.3605. In part B, what is the probability that a random sample of 20 pregnancies has a mean gestation period of 143 days or less? In this case, we have a sample size of 20 and everything else is the same. So we'll go to the computer to try this out. In part B, enter the sample mean of 148. Now for the standard deviation, you have to do a workaround. For the standard deviation, sigma of x bar, this is equivalent to sigma divided by the square root of n. So I enter 14 divided by the square root of 20. And I calculated that number to be 3.130495. Enter that for the standard deviation, and then select below 143. So that's the most difficult part, is to calculate the standard deviation, and you use this formula here to calculate the standard deviation. After that, click recalculate, and then here's your probability. We have a 5.51% chance if we select 20 pregnancies that their average would be less than 143 days. In part B, we have the probability that x bar is less than 143 is equal to 0.0551. Part C, what is the probability that a random sample of 49 pregnancies has a mean gestation period of 143 days or less? In this problem, we have n equals 49, and I'm looking for the probability that of these 49 pregnancies, we have a sample mean that's less than 143 days. And so we'll do this on the computer. For this problem, enter the mean of 148, and for the standard deviation, I use the same formula. The standard deviation of the sample mean is equal to sigma divided by the square root of n. 14 divided by the square root of 49 gives me exactly 2. So this is where the 2 comes from. That's the most difficult part, is to calculate the standard deviation for the central limit theorem. Once you put that in, everything else is the same. Click below and enter 143, and here's our probability, 0.0062. We have the probability that the sample mean will be less than 143 is equivalent to 0.0062. If you look at part A, we are selecting one person out of the entire population. What's the chance of that one person having an average less than 143 days? Well, we know the average of the population is 148, so it's not that difficult to get. It's 36.05% chance. In part B, we're selecting 20 pregnancies, and I'm saying if you take those 20 individuals and take their average, what's the chance of them being 143 or less? Well, that's a lot harder to get. Remember, the population has a mean of 148. So we're saying, what's the probability of selecting these 20 pregnancies and having their average less than 143 days? That's a little bit harder to get. So we have only a 0.0551 chance of that. And in part C, we're saying, what's the chance of getting 49 pregnancies whose average is 143 days or less? That's even more difficult to do. As the sample size increases, as this denominator gets bigger, this number actually gets smaller because you are dividing by a larger number. What we are saying is the standard deviation gets smaller as the sample size increases. That's why our probability gets smaller as the sample size increases.